Hello everyone, in this video I'm going to study the electromagnetic induction. What is the electromagnetic induction? Electromagnetic induction is the production of an electromotive force, EMF, across an electrical conductor in a changing magnetic field. When a bar magnet moves toward the coil, if that is north and south, this is a bar magnet. When it moves into a solenoid, moved toward the solenoid, so what will happen? EMF reduces in the coil because we have a change in magnetic flux. That change in magnetic flux produces a current in one direction. So the galvanometer needle, if we connect that wire to a galvanometer, so what will happen? The galvanometer needle deflected to the right. When the north pole or the magnet moving away from the coil, so when that north pole moving away, what will happen? The magnetic flux changes and EMF induced produces a current in opposite direction. So the galvanometer needle will be deflected to the left. What will happen in the current in the first case? In the first case, when we move the bar magnet into the coil, the north pole into the coil, so if we represent the relation between the current and the time, so when we represent that relation, so we will get here the current pass through the wire in one direction. When we pull the north pole away, the current will be reverse. So in the second case here, the current will be reverse. When we represent the relation between the current and the time, so what will happen here? The current move in opposite direction. Now what will happen if we move the north pole completely inside the solenoid? So when we use this way and we move the bar magnet completely inside the solenoid, what will happen? So we will get this relation between the current and the time. So the current varies from positive to 0 to negative, to 0. But actually, because it's just one complete cycle, so it's just between the current moves from 0 to maximum to 0 to minimum to 0. Let us start the experiment. Apparatus, center 0 galvanometer, coil of about 20 turns, magnet, bar magnet, connecting wires. The procedure. Set up the apparatus as shown in that figure. Now we connect the circuit. Thrust the north pole of the magnet into the coil and record your observation. So what do you notice? The galvanometer needle deflected to the right and then to 0. We register this observation. Now this is the observation. Galvanometer needle deflected to the right. What happens to the magnetic flux in the coil? Actually, what will happen to the magnetic flux? When we move the bar magnet into the coil cuts the magnetic field lines. So the magnetic flux changes. That change in magnetic flux in the coil produces EMF in the coil. That EMF produces a current in the wire. So the galvanometer needle deflected to one direction because the current passed through in the wire in one direction. The second step, when the bar magnet stop in the coil, no change in flux. So no change in flux, so no EMF produced in the coil. So no current produced. Observation, no change in magnetic flux. Step 3, pull the north pole of the magnet back out of the coil. The galvanometer needle deflected to the left and then returned to 0. So the observation, galvanometer needle deflected to the left. What happens to the magnetic flux? The magnetic flux changed, produces EMF in opposite direction and the current reverse. So what happens to the magnetic flux in the coil? Changed. Step 4, move the magnet faster in and out of the coil. So the galvanometer needle deflected from right to left, faster. And the deflection is more than the previous steps. What about the observation? The change in magnetic flux is more, produces more EMF than before, and it will be reverse from both directions. So the current also will be reverse. Step 5, move the magnet through the coil from one end to the other, from this end of the coil to the other. It starts from 0 and then deflected to the right and then left and then 0 again when the bar magnet go through the coil from one end to the other. This is actually complete cycle from 0 to right and then to 0 to left to 0 again. One complete cycle. What happens to the magnetic flux in the coil? The magnetic flux changes from one direction to the other direction. Give us one complete cycle for the current. Step 6, put more turns on the coil and move the magnet faster. Actually, we have just one coil of 20 turns. When we add more turns, the deflection will be more. Why? Because the EMF induced in the coil depends on what? Depends on the number of turns of the coil, depends on the magnet. So how can we increase the EMF induced in the coil? Increase the number of turns of the coil, increase the cross-section area of the coil, move the magnet faster, or use a stronger magnet. Step number 7, repeat step number 1 by using the south pole of the magnet. Now we use the south pole. So what will happen? The deflection will be opposite to the deflection in step 1. The deflection it will be to the left and then return back to 0. So this is the observation and what happened to the magnetic flux. Now analyze this. So this is the analyze. The magnitude of EMF induced in the coil is directly proportional to the rate of a change in magnetic flux linkage. I hope you understand this experiment. Thank you.